Black holes are in many ways the most extreme objects in the universe. They literally pack an enormous amount of mass into a smaller volume of space, bending the fabric of space so much that once something enters a certain area, it can never escape, even if it travels at the ultimate cosmic speed, the speed of light. Apparently, there are trillions of black holes distributed in every galaxy universe, with the most enormous ones reaching billions of solar masses. And yet, if we think about how all these black holes were formed, we can say quite confidently that each of them was originally made of ordinary matter. None of them were formed from dark matter, even though dark matter outnumbers ordinary matter a 5:1 ratio in the universe. But if black holes are the result of gravitational force, if dark matter responds to it, then what prevents a black hole from forming from dark matter? Today, we have a cosmic story about whether black holes can be composed of dark matter, and if not, why not? There are only a few known ways for black holes to form in our modern universe. Perhaps the most common method is the collapse of the core of an extremely massive star. The only thing that keeps stars from gravitational collapse is the energy produced by nuclear fusion in their cores, where the external radiation pressure balances the internal gravitational force. When the star's core runs out of fuel to burn us, the pressure and radiation begins to drop, and the star's core begins to contract under its own gravity. As the core of the star is compressed, it heats up to temperatures that are even hard for the common viewer to imagine. The higher the temperature becomes, the more likely it is that the core can begin to burn even heavier elements, using them as fuel. And once those elements are exhausted, the core will collapse into a Type II supernova. And if it's massive enough, a black hole will form, due to the buildup of enormous mass in such a tiny amount of space. If the nucleus is not massive enough, a neutron star will be born. In addition, a black hole can still be formed by the collision of two neutron stars, provided that the total mass, after the merger, exceeds a certain threshold. Finally, a black hole can form because of a direct collapse, when, for example, a single massive star simply becomes too dense for light to escape from a certain volume of space. Once this condition is met, an event horizon is formed, and anything that crosses it is guaranteed to not only never escape, but to rapidly increase the mass and therefore the size of the black hole that forms. In a short time, it can absorb the entire mass of any object from which it formed, and then a black hole will also appear. Of course, there may be other exotic ways of black hole formation, but it is believed that the above are responsible for the vast majority of existing black holes in the observable universe. As you may have noticed, all these methods have something in common. They are based on ordinary matter, consisting of atoms and their components. This becomes even more surprising when you consider a few facts. Normal matter makes up only 1/6 of the total mass of the universe, while dark matter makes up the remaining 5/6. Both normal and dark matter experience gravitational force in the same way, just as obeying Newton's and Einstein's laws of gravitation. In any environment where there is an abundance of normal matter, such as a Milky Way like galaxy in general, there is significantly more dark matter with a ratio of at least 5:1. But why then can normal matter form black holes so efficiently, but dark matter cannot? The key lies not in the force of gravity, but in other forces. Things like friction and collisions, which depend on electromagnetic interaction. Ordinary matter experiences this force. Dark matter, on the other hand, does not. When a galaxy forms, dark matter and ordinary matter tend to form in it in the aforementioned 5:1 ratio. On average, this is the case throughout the cosmos. Like all particles under the influence of gravity, both matters are attracted to the center of gravitational potential, and in that direction, they accelerate. But here's where the fun begins. When dark matter travels through a galaxy, there is no friction, no heating, no interaction with electromagnetic radiation, and no way for it to exchange energy or momentum with other existing particles within the galaxy. It would remain in a slow orbit with high angular momentum, and it would probably take about 1 billion years to form a single complete ellipse. Ordinary matter, on the other hand, has everything that dark matter lacks. It collides with other baryonic matter particles that can exchange energy and momentum. The particles can collide, causing them to lose kinetic energy and angular momentum. They experience friction, heating up as they interact with other particles of ordinary matter, reacting to radiation. Well, collectively, all these phenomena lead to a serious difference, which can be summarized as follows. Ordinary matter loses momentum and angular momentum and sinks into the galactic core, whereas dark matter always remains diffusely distributed in a vast space, creating a halo around the galaxy. Ordinary matter forms single, dense, small clumps, while dark matter forms sparse clumps, but mostly very large in size. Without a mechanism by which it can transfer angular momentum, dark matter can never even approach the density necessary to create an event horizon and hence a black hole. Dark matter stars do not exist. Therefore, dark matter cannot have a core collapse. There are no regions that would ever collect enough dark matter to attract light in that region and back onto itself, which means there can be no dark matter that has undergone a direct collapse. And there are no stellar remnants or other relatively dense objects made of dark matter. And therefore, there is no way for collisions between dark matter-rich objects to result in the formation of a black hole. All mechanisms by which ordinary matter can collapse into a black hole do not work in application to dark matter. Now it becomes clear that when a black hole is formed from ordinary matter, dark matter particles cannot cross the event horizon and increase the mass of the existing black hole. In this respect, dark matter is no different from any other form of matter or radiation. When crossing the event horizon, everything will inevitably fall into the central singularity and eventually increase the total mass of the black hole. But because of the lumpy nature of ordinary matter and the diffuse nature of dark matter, there are no realistic scenarios in which even 1% of the total mass of a black hole could be derived from dark matter. In fact, based on what we currently understand about the universe, there is only one possibility of ever creating a black hole from dark matter. This would only happen if the very early universe had fluctuations of large enough magnitude that it would quickly collapse to form a black hole long before stars formed. If this were to happen, it could create one or more primary black holes that would exist independently of stars. This is the one case where only mass matters. Since the calculation is based solely on the physics of gravity and the way structure forms in an expanding universe, it allows us to determine how much excess density is needed to form a primary black hole. Regardless of the average density, if the universe is born with an area that is locally 68% larger than a given average density, this will lead to gravitational collapse and the formation of a primary black hole. And now we have a universe that is born with a spectrum of fluctuations, and these fluctuations produce the structures that we see everywhere in the universe. We see the effects of these fluctuations in temperature defects in the cosmic microwave background, signatures of the cosmic microwave background, in features such as correlation functions and power spectra of the large-scale structure of the universe. When it comes to scientific conclusions, it is important to ask the right questions. Regarding dark matter and how we understand it, we can expect that there are no black holes in the universe today, or ever consisting mostly or exclusively of dark matter. There are no stars, supernovae, stellar remnants, or direct collapse scenarios that should have resulted in a black hole composed of this matter. And there is no way that this matter was dense enough to form a black hole after the universe began its existence. Unless we turn to new but unobservable new physics to cause the creation of a certain spectrum of primary black holes composed of dark matter, we can safely say that it is ordinary matter, not dark matter, that is responsible for the black holes we see in our beloved universe today. Don't forget to give this video a thumbs up, subscribe to the channel if you're not already with us, and see you soon.